This is going to be a short video on the derivative. I'm going to cover what the derivative is, how it works, and how it is used, and the different forms it appears in. We're going to start with what the derivative actually is. The derivative is pretty much just a slope and or a rate of change. Another way to describe it is that the derivative is just a tangent line. And a tangent line is pretty much just a line off of a curve that has a given slope and y coordinate. Pretty much what that means is that on any sort of graph that has a curve, you're able to find a slope at any given point of x. This is really related to the equation y2 minus y1 over x2 minus y1, the standard slope equation. This is a way to find that slope at any given point of x without having 2 points. Just to recap, the derivative is used to find the slope of the tangent line of a curve at any given point of x without using the standard slope equation y2 minus y1 over x2 minus x1. This is a really powerful thing to do, and I'll show you examples later. But first, I'm going to show you how the derivative is derived, starting with the definition of the derivative. There's a bunch of different forms for the derivative. The most basic ones are f prime of x and dy over dx. Both of those are the derivative. The actual definition of the derivative is the limit as x approaches h of f of x plus h minus f of x over h. That may seem like a lot, but I'm going to explain how that's derived right now. Imagine a graph with a simple curve, and then put 2 random points on that graph. I'm going to label them as p and q. If we give p a random coordinate of x, then the distance between p and q is going to be the change in x. That means that the x coordinate for q is going to be delta x plus x. Now the y coordinate for p is going to be f of x, or y, and the y coordinate for q is going to be f of x plus the change of x. What this gives us is a universal graph with any given x or y coordinate on any given curve. We're going to use this to find the slope of any point of x. So if you look at this secant line I drew very poorly, I'm labeling it as the slope because that's the slope between the point p and q. This is also a universal slope. So if we have an arbitrary point p and q, we can plug in any coordinates here and we'll get the slope between the 2 points. Now if we take that same graph and that same concept and we write out the equation, and then we repeat it over and over again, but this time making q closer to p. The goal here is that we make q infinitely closer to p to the point where it's actually just 1 point. Well, what happens there is that the change in x between the 2 points ends up becoming 0. So what we're actually finding is the limit as the change in x between the 2 points approaches 0. And then we plug in the basic y equation using f of x plus the change of x as y2 and f of x as y1. If we end up simplifying this equation and substituting delta x as h, we end up finding the definition of the derivative. And this is a really powerful tool, because what this lets us do is we can plug in any point of x into this equation, and we'll get the slope of the tangent line at that given point. This has an enormous amount of applications. To list a few, we can use the derivative to find the instantaneous velocity of any sort of moving object, or we could also use it to find the rate of change of an equation giving any sort of increase or decrease in quantity or distance. We can also use it to find the maximum or minimum of a graph. Right now I'm going to show an example of how to use the derivative to find the instantaneous speed of a ball being dropped from the top of a building. So let's say there was this kid on top of a very large building. He was holding a ball over the side of the building when he decides to drop it. So the ball went from rest and is now being pushed by gravity towards the ground. The position of the ball is given by the equation S of t is equal to 4.9 times t to the power of 2. And pretty much that's just a basic exponential equation of a ball being pushed by gravity downward. And it's represented by this graph here with position over time. And the conclusion is that by using the derivative, we can find an equation that will give us the velocity of the ball at any given point. We can use this to find the initial velocity and also the final velocity right before it hits the ground. So we start off finding the velocity equation by writing that S of t is equal to 4.9 t squared, and then using the definition of the derivative by plugging in 4.9 t squared as f of x. This is it written out, and we're going to simplify it. By simplifying it, we'll be ending up getting the slope of the tangent line. And by doing that, you can plug in any point of t, and you can get the velocity at that point in time. At this point, I've done some basic simplification, and now I'm at the limit as h approaches 0 of 9.8t plus 4.9h. And because its limit as h approaches 0, you can make 4.9h equal to 0, which leaves you with 9.8t is equal to the velocity equation. So v of t is equal to 9.8t, which means that at time is equal to 0, the ball was not moving. And when the time is equal to 10, the ball is moving at 998 meters per second. Now, meters per second is arbitrary because I never actually put units into the equation, but it helps you see how powerful the derivative is. It can be used to find the instantaneous velocity of anything given the equation of the position of an object. That's just a small example of how the derivative can be used. I hope that this video is helpful.